so we'll be able to kind of catch up with it, and hopefully we'll finish within a timely period of time. So my name of my talk that I'm giving today is Everything You Wanted to Know About 3D Graphics But You Were Afraid to Ask. So here's just a little bit about myself. If you haven't come up and talked to me at all yet today or during this conference, I recently finished up working on a book on 3D graphics programming called The Metal Programming Guide. It's available to pre-order on Amazon. If you follow me on Twitter, I have a pinned tweet that has a link to that book. But so I started programming about 4 or 5 years ago, and back when I started programming, I'd come from a journalism, like videography, audio engineering background. And when I started programming, one of the things that my teacher always told me was that graphics and audio were like the hardest things that you can do in programming. So like I wanted to show that I was like a badass computer programmer, and so I was like, okay, I'm going to learn graphics because everyone says that it's really hard, and I'm not afraid of hard stuff, and I'll show everybody like what an awesome graphics programmer I can be. So I went out and bought a book on OpenGL, and I started reading this book, and I was just like, what? So like I was reading through this book, and just like it talked about like GL clear color, GL like whatever, GL, but it didn't really give me any idea about what any of these things were actually doing. So like I could go and I could work through like I could read this book and I could kind of like answer you questions about OpenGL, but I really couldn't tell you about how to do anything useful with them. And kind of like over the years, I kind of figured out that graphics is kind of a multidisciplinary thing, and that you have to know graphics concepts, you have to know an API or framework that deals with graphics, and then you also have to understand a lot of mathematical stuff associated with graphics. So I started to a lot of stuff kind of got in the way. Like I'd been interested in metal when it was introduced in 2014, but then Swift came out, and I had a bunch of other projects going on, and I kind of felt like I missed my chance to go out and be the metal expert person, and I figured somebody else was going to pick it up, and after 3 years, no one really had yet. And I kind of realized after trying to learn this a couple of times, there were a bunch of places where people tended to get lost and they got stuck. So like they would go in and they would try to learn the like low-level buffer and Vertex stuff, and they go, well, this is boring, this is like boilerplate stuff, I want to write shaders. Then they'd go to write shaders, then they'd find like the blend-fong like per vertex lighting algorithm. They'd see all this weird like crazy linear algebra. They'd be like, okay, this is way too complicated, I can't figure this out, I'm going to go back to core data. So kind of the point of this talk was just kind of like I tried and failed several times to learn graphics programming until I finally figured out where I kind of would give up and what things tended to confuse me. So this is just kind of the basis of my experience of what it was like for me to learn graphics programming. So I'm going to tell you a bunch of stuff that I wished that I had known when I started graphics programming, and things that would have made it a little bit easier for me to get into doing graphics programming. And I was kind of hoping that there would either be time or this would be a smaller room, and that people would be able to like tell me questions that they had that they were afraid to ask. But like I'll be around for another couple of hours after this talk is over, so I'd really encourage people to come up and tell me about their own personal questions that they have. So this talk is basically all of my questions that I had and things that I wished that I had known when I got into graphics programming. So the first thing that I want to talk about was like trying to figure out how to actually even think about what graphics are. So like one of the reasons that I had problems with getting into graphics with OpenGL was that I was really like all of the books really approached it as talking about like an API that had a bunch of different commands and a bunch of different terminology and stuff like that. So I never really could wrap my head around what exactly are graphics. So for this particular part of the talk, I'm going to use color as an example, but this applies to everything in graphics. It applies to positions, it applies to shaders, it applies to everything. So color is a natural phenomenon. We have a visible light spectrum that goes from 400 nanometers to 750 nanometers. That goes from like deep purple to very deep red. So like we have, this is a physical phenomenon, and we need to find some way of being able to model this in a way that the computer can really understand. So we need to find some way of being able to quantify this color spectrum in a way that it can be understood and processed by the computer. So I'm going to talk a little bit about how the computer actually understands and is able to deal with and understand data. So the computer, everything comes down to binary. It comes down to like ones and zeros. So back in the olden days when they had the Apple II only had like a 2-color screen. Everything was either on or was off. So you only had 1 bit of data that was available to represent colors on a screen. So now, like, I'm old, so I remember back when, like, color monitors first came out, you had, like, 256 whole colors that you could see on the screen. So, like, around the time that they started being able to have color monitors, they were able to have 8 bits of data to represent all of the colors on the screen, and that gave you a lot more options of being able to show a couple of different colors. And then as years went by, you had thousands of colors and millions of colors, and now they don't even bother to tell you how many colors you have on the screen because it's just assumed that everybody has like these millions and millions of colors. And the way that that was able to be represented on the screen was some computer scientist at some point determined that, well, not even a computer scientist, a scientist in general at some point determined that all visible light that we see as human beings could be represented in some percentage of red, green, and blue light. So they were able to figure out that if you had reds, greens, and blues, that you could combine all of these in order to be able to mimic and represent the visible color spectrum that we looked at earlier that was done in like nanometers or whatever. So because you're able to go in and have everything represented as a color on a screen as being some percentage of red, green, and blue, that means that you're able to actually quantify what you have for red, green, and blue. When you only had 1 bit that was available to actually go in and like look at the colors on the screen, then you had black and white. Then when you had 2 bits, you were able to double that and get it to 4, then 8, and 16, then finally 256. So like if you go and have ever worked with Photoshop and you look at the colors in Photoshop, everything in there has some percentage, like when you have red, you have like some value between 0 and 255, which means that Photoshop has 8 bits of data associated with the red, 8 bits of data associated with the green, 8 bits of data associated with the blue. So every single red, green, and blue can be represented as some value between 0 and 255. And because you're able to go in and actually represent every single value as some numerical value and quantified between 0 and 255, that means that you're able to actually go in and perform mathematical algorithms on those values. So one of the kind of like entry-level image processing shaders that's available out in the world is a desaturation shader. And this one is takes into account the fact that human beings see luminosity a lot more precisely than they do like color. And luminosity can be better represented on the computer using the green values for the pixels. Like some computers have more like 2 green pixels for every red and blue pixel. So this goes in, and because you're able to represent each color as a value of red, green, and blue, you can multiply it by a couple of values and then sum them together in order to create a grayscale black and white image. As you can see here, every single pixel in this image had this algorithm run on it, and then those values were summed, and it gave the grayscale value between 0 and 255. You were able to actually get a grayscale image from a color image. And it, again, like I said at the beginning of this talk, this doesn't just apply to color. This applies to position data. This applies to any type of signal processing that you want to do using a computer. Again, I'm old. I remember back when CDs first came out, and CD's quality sound was always 44.1K and 16-bit, which means that every single second of audio that was on that CD had 44,100 little snapshots of where the waveform was at that particular moment in time, and it had 16 bits of data that were available to express the value of that waveform. If you go back and you listen to like 8-bit audio from like the original Nintendo, it doesn't sound realistic. It sounds very weird because it only has 8-bit, it only has 256 values that can express what a waveform looks like, as opposed to however many values you have with 16 bits. So the more bits that you have, the better fidelity that you can have in order to be able to express values. And at some point it was kind of determined that 256 values for the red, the green, and the blue were probably sufficient for everything that you wanted to see. And there wasn't really any point in adding any more to that. So basically, everything that you deal with in computer graphics has to be deserialized in some way to make it quantifiable using some kind of number so that the computer can go and perform algorithms on it. So I've talked a little bit about how the basis of graphics programming is performing algorithms on this data. So you might be wondering at this point, well, how do we do that? How does that fit into computer graphics and being able to apply algorithms? And the place where we go and we apply algorithms is in the shader program. So how many people here have heard of shaders? Okay, good. I've had a talk where somebody's like, what's a shader? And I was like, oh God, no. So every single type of graphics programming, it doesn't matter if it's OpenGL or DirectX or Vulkan or whatever, has a graphics programming pipeline. So a bunch of Vertex data is encoded into this pipeline. It is sent to the Vertex Shader. Processing is done. Sometimes you have a tessellation shader, sometimes you have a geometry shader. Right now there are no geometry shaders in metal, but that might be something we do in the future. That process is rasterized and sent to the Fragment Shader, which is then output to the frame buffer, which will then display it to the screen. This isn't necessarily important to remember all of this right now, but this is just kind of the general idea that you have some kind of data that you've encoded on the CPU that is sent to a shader that performs processing on it, that sends it to get it kind of put together, which is then sent to another shader that is output to your screen. So what are shaders? Shaders are small programs that take over the responsibilities of different parts of this programmable pipeline. So back before OpenGL 2, all of these things were kind of hard-coded, and there were very limited amount of things that you could do to change all of the data that was being passed through this pipeline. So now you are responsible for that, and you can go in and you can get a lot of really interesting and complex effects that weren't really possible before they had the programmable pipeline. And if you're working with graphics in, like, be it Metal, Vulkan, OpenGL, whatever, you're responsible for two steps of this process. You're responsible for the Vertex Shader and the Fragment Shader. So the Vertex Shader is first, so I'm going to talk about that one first. So what the Vertex Shader does is it translates all of these positions that you send in through the vertex buffer from object space to world space. So I'm going to use the dog as an example. I got her to sleep, so she's going to real crappy right now. So let's pretend that we're trying to recreate the dog. We're trying to express the dog in some kind of quantifiable way. Pretend like the dog's kind of in an invisible box, and that the center of the dog is the center of the box, and that there are various corners of the box. You can express all of the different points that make up the pug in some kind of relative way between the center of the box and the box that encloses the pug. So everything will be something. In most of the graphics programming paradigms that I've used, the values are between like -1 and 1. So the center of the pug would be like 0, the tip of the pug's nose would be at 1, and then the tail would be -1. And so every single point within there is some value between -1 and 1. Yes, you can go back to sleep now. So I can go and I can create a model that expresses the dog within this object space where every single point of the dog is between -1 and 1. However, if I wanted to recreate this room and create the scene, and I had this pug, like, I need to find some way of being able to express the pug between object space and world space. So like the imaginary box the pug exists in, that's her object space, and this room is her world space. So when I want to go and import the pug into my graphics program, I don't want her to take up the entire room. She's not going to be the size of this room. She's going to be little. So one of the things that the Vertex Shader is responsible for is translating all of the different points of the pug from her own object space into a bigger world space. So it'll scale her down, it'll rotate her, it'll kind of like move her around, so that way I can express that instead of taking this entire room, that she's pug-sized, and that she's up in the front left corner of the room. Another thing that the Vertex Shader is responsible for is determining what is and is not going to be rendered to the screen. So pretend we've all seen like the 3-camera sitcom thing where you have like a stage up front and you have people talking, and then kind of behind the cameras and everything is a studio audience that nobody sees. So this is the projection matrix. And what the Vertex Shader does is it determines how much of a scene is actually going to be rendered to the screen. So, like, for me, like, I see all of you guys, but the people in the front row, they don't see anybody behind them. So if the projection matrix is facing forward, the computer program would determine that it needs to create the stage and the pug and the podium and me, but it doesn't need to create all of the people that are behind the people in the front row, because even though they exist, you don't see them, and so you don't need to invest a whole bunch of processing power into rendering all of these people that are not being seen to the screen. So like every single frame of the video goes through, looks and sees what's actually inside this projection matrix, and it ignores everything that's outside of it. And then there's other processing that you can do on the Vertex Shader. You can add some vertex lighting, but basically the whole point of the Vertex Shader is to go in, determine where everything is supposed to be in the room, in the scene, figure how much needs to actually be produced, and then it passes that to the rasterizer. And the rasterizer kind of like assembles all of this stuff together and then passes it to the Fragment Shader. So the Fragment Shader is responsible for determining what color every single pixel that is being rendered is going to be. The Fragment Shader is where you would apply different algorithms like the saturation algorithm, the lighting algorithm, and you can chain a bunch of these various algorithms together. So like if you had a scene that had 3 different lights in it and you had a base thing that was like purple, you would set the color to purple, and then you would apply an algorithm to it for 1 bit of lighting, and then the next bit of lighting, and then the 3rd bit of lighting, and then whatever that color actually was determined to be would then be output as the output to the Fragment Shader. So this will allow you to go in and do a lot of really interesting and intricate effects. And it isn't just going in and doing like texture. It isn't just going in and applying like colors and lighting. You can actually go in and apply texturing. So like one of the things that I didn't really understand that I'll talk about a little bit later was that a lot of the video games that you play, that all of the different like geometries and stuff you see, they aren't necessarily like rendered algorithmically. They can be applied as texture. So one of the responsibilities of the Fragment Shader is to keep an eye out between what image you're trying to apply to the object that you're rendering, and how that, whatever color is in that texture, and how it will apply to the object. Again, I'll go into this a little bit more detail later. But the Fragment Shader is responsible for figuring out what color every single pixel is going to be in an object. So I've talked a little bit about how you have all of these, you have the pub exists in its object space, and how you have a bunch of vertex data that gets passed into the shader. So you might be wondering like how that actually happens. So back when I was starting to learn OpenGL, there was always the same tutorial that everybody would do, where you create this multicolored like spinning cube. And this is something I was kind of embarrassed about, but I thought because when you did these tutorials and you went in and you entered all these vertices by hand, that was the way that you did everything. So if you played something like Mass Effect and you had a character like Shepard, that somebody had actually gone through and hand-coded every single vertex that went into Shepard, and I was just like, oh my god, how did people even do this? This artisanal way in, okay, the nose looks just a little bit off. I have to go back in and find a 1,373rd vertex and I need to change the Y value slightly, because I didn't really see how you got these really big complex models into an application. What it is that you have model files that you can create in Blender, in Maya, and in other programs that go and express in some coded fashion all the different data that you want to pass into a Vertex Shader. So this is an object file for the Utah teapot that was created in Blender. So in this particular screenshot, you're seeing this is a description of all the vertex data that exists within the teapot's object space. And object files can include different information for vertexes, for colors, for lighting normals, or for other information that you need in order to be able to recreate this teapot in another program. And there are a lot of different types of files for this. I think Apple's Model I/O framework supports Alembic. It supports, I think, 5 different formats. So some of them are human readable, like this object format. Other ones are weird computer binary stuff that you wouldn't really be able to open up the text editor and be able to understand. But that's how you're able to actually go in and get really big, complex, lighting models and animations and huge, complex things into your applications. So I mentioned a little bit earlier when I was talking about fragment shaders, I mentioned a little bit about texture mapping. So if we've ever played a video game, one of my favorite games when I was a kid was Myst, and everything in Myst was incredibly graphically complicated and very realistic. A lot of 3D graphics stuff, you have a bunch of things that look like they have a lot of geometry, but going and rendering a lot of geometry is incredibly computationally expensive. So if you're going down a street, you have buildings on the other side, and you're going in and actually rendering out where all the windows are, where all the different bricks and everything are, that would be very expensive, but it's something that you're not really going to notice because when you're playing your game, you're kind of focused ahead of you, and it's just kind of stuff in the background. So one way that computer programmers have figured out to actually go in and add a lot of realism without having to deal with all of the computationally expensive geometry is to apply textures to objects to mimic this geometry. So like one of the really common use cases of going and making crates. So you can just have a nice simple box that only has a couple of vertices, and then you can apply this texture that looks like a box to this crate so that it looks like it has all this geometry. It's made out of wood and it has its shadows, but you only have to render out the box, and then you just have to do like a texture sampler where it goes and it checks between the image and the box of what color every single thing in the box is supposed to be. This can be done with shadows, and it can be done with other things that are incredibly expensive for the computer to go in and actually compute. So, like, if you go and you have a really complicated, character that you've created in Maya, you'll export the texture atlas that will have all of the different textures associated with that character, along with a correlating key where the Vertex and Fragment Shaders will be able to figure out what how each of these different pieces actually fit onto a character. So this allows you to go in and be able to actually create very complicated looking characters and objects without having to incur a lot of expense on the GPU. So I started off this talk kind of talking about how I kind of failed to learn graphics programming because there's a lot of stuff associated with it that was incredibly difficult to learn and understand. So one big thing I've seen a lot of people do when they get into graphics programming that I recommend not doing is a lot of people, they jump directly down to the metal. Instead of going and trying to learn some kind of higher level abstraction, they'll go and say I'm just going to learn metal. And then they get into it and they realize that there's a whole base of knowledge that they don't really understand, and it's assumed that you understand because there's an assumption that you've either worked with OpenGL or you've worked with some other thing that has made it easier for you to go in and actually learn graphics programming. So if you're interested in graphics programming, I'd still like you to buy my book because I spent a lot of time working on it. But I have a few other recommendations for if you're getting started with graphics programming about what you would try instead of jumping directly to metal. So for iOS, Core Graphics, Scenekit, and Core Animation are really good abstracted frameworks. So I talked to somebody who was on the Metal team at Apple, and I said to why would anybody use Metal for 3D graphics stuff if they have Scenekit? He's like, well, the point is that you're supposed to use Scenekit. You're only supposed to drop down to Metal when you encounter something that you can't do in Scenekit. So anytime you want to work with graphics, try to find the highest level abstraction that you can find that will allow you to do what you want to do, and then try to make whatever the lower abstraction level is, work with the higher level abstraction. Try to do all the easy stuff that you can in this higher level abstraction. One of my favorite quotes is from Larry Wall, the creator of Perl, where he said, "Easy things should be easy and hard things should be possible." So don't make things harder for yourself by jumping directly to OpenGL or Metal or Vulkan or whatever. Another framework that I found to be really decent for teaching 3D graphics concepts was 3D.js, JavaScript. But I found that to be a very incredibly well done framework. It's an abstraction over WebGL, and it works the way that I would have expected graphics to work, where you don't have to go and spend 40 lines of code setting up buffer and a vertex and a bunch of other stuff. You just go in and say, hi, I want to create a mesh. I want this mesh to be cube shaped, and I want it to have a matte appearance, and it will just do it. That'll give you a chance to actually go in and get familiar with some of this terminology and some of these concepts before you have to go in and try to create them yourself at this really lower level. Another really good framework is processing. Processing was created by a man named Daniel Schiffman. He wanted to create it for people who were artists, and it's basically kind of like the Arduino of graphics programming. So it's intended for makers and people who weren't necessarily computer scientists who wanted to be able to go in and do really cool, complicated graphics programming stuff. You can put processing on a Raspberry Pi, and you can set up a touch screen to it, and you can interact with it, and it's a really good entry-level framework that gives you an idea about all of these concepts without forcing you to do everything the hard way. Also, just working with Unity or Unreal will give you a good idea about how to, at least with complex terminology and concepts and how things actually kind of work and function so that you can kind of go, okay, I know I can do this in Unity, and how do I recreate this in Metal? And then last one I wanted to recommend is Shader Toy. Shader Toy is a WebGL site that allows you to go in and write really complex fragment shaders. And people have done some really incredibly awesome things just with the fragment shader. They've gone in and done really complex drawing and it mimics animations and stuff. So like going there, even just to look at what other people have done and look through their code, it's a really awesome resource to go in and learn fragment shaders. So now I've kind of talked to you a little bit about things that got me kind of, caught up and what I recommend. So here's some first steps for if you're interested in getting involved in graphics programming. I had originally intended to set up an entirely large math section on this talk, but I realized it's like the last day of the conference, everybody's tired and hungover, and also you can't really cover a lot of math in like 5 to 10 minutes. So starting points I would have for people is go back and try to get refamiliarized with trigonometry, because so much of what we do with graphics programming is built off of concepts from trigonometry. So get familiar with sine and cosine and get comfortable with knowing what those are, so that when you go and you look at an algorithm that mentions sine or cosine, you don't just go Then again, a lot of those concepts from trigonometry are built upon in linear algebra, specifically in matrix transforms and dot products. So I would recommend just kind of going in. I have a chapter in my Metal book where I talk about these graphics concepts. I was told that was going to be made available for free, so at some point when it's up, you might be able to go through and read through that. And I kind of detail a lot of how to think about the trigonometry, how it leads to the linear algebra, and how that interacts with how things work within graphics programming. So just a couple of good resources that I found for getting familiar with these graphics programming concepts so that you could be more comfortable with the math. There's a really good Udacity course from Eric Haynes. Eric Haynes wrote one of the seminal books on graphics programming, ray tracing. And he's been doing this for 20 years, and he actually is one of the few experts who's really good at explaining what he does in a way that most people can understand. So this was a really awesome course that's available for free on Udacity, and I highly recommend it to anybody who's interested in graphics programming. And the other one that I want to recommend is the book The Nature of Code. That's by Daniel Schiffman, the guy who did processing. He uses processing as kind of his basis in his book, but it explains a lot of really interesting and cool concepts like fractals and how neural networks work. And he does that in an approachable way with not assuming that you know a whole bunch of stuff, because he assumes this is for makers and not necessarily for programmers. So kind of last thing that I want to go over is I want to give a little bit of encouragement. So I spent 4 years trying to get into graphics programming. I took a year off of my career so that I could go and really dive deeply into learning graphics programming. And I've seen so many people, when they encounter something that's a little bit hard, they don't necessarily understand right away, they just kind of think, well, you know what, this isn't for me. I'm not smart enough to figure this stuff out. I'm just going to go back and do something that is less hard. And the thing is, our brains are these amazing things where I had to read a bunch of stuff 4 or 5 times before I was able to understand it. I went back and I read that OpenGL book that I read a couple of years ago that I thought was just absolutely horrible because it didn't explain anything. And I'm looking at it now, I'm like, wow, I don't know how this could be more clear. This is a really good book. But it took years for me for my brain just to kind of rewire and get comfortable with all these things and process it. So the first time you encounter something that you don't really understand very well, it's not going to make any sense. You're going to feel like an idiot. But if you keep pushing on it and you keep trying at it and you spend several years bashing your head against it, your brain eventually will figure it out. So I don't want anybody to feel like they can't do something because they didn't pick it up in 10 minutes and they were awesome at it. If you're really passionate about something, you can learn anything that you want to if you give it enough time and you're stubborn enough and you just keep bashing away at it. And yeah, there's no magic resource for learning computer graphics. So again, I read a book a couple of years ago that didn't make any sense. Now it makes a lot of sense because I've had enough time between now and then to go in and actually learn stuff. So the first thing that you read probably isn't going to make a lot of sense. But after a while, after you think about it for a bit, you'll start to go, okay, it doesn't make any sense, but I have a very specific question about this one thing that I keep seeing. And that gives you kind of a grasping point where you can can go in and go, okay, I don't understand all of this stuff, but I want to figure out this thing. And then when you figure out that thing, that leads to other things. And eventually, after a couple of years, you start to know a lot of stuff. So just know that you have to like look at things over and over again in order for them to make actual sense. And again, don't jump into the hardest thing that you can possibly do. You know, like this is hard enough already to do on your own. So you know, take baby steps. Try to make things as easy for yourself as possible. Like if you're interested in 3D graphics, go look at Scenekit. Go look at play around with more animations. Try to find ways of making it easier to kind of like wade in and try to figure this out rather than jumping to the hardest thing that you possibly can. Because like learning something really hard is like it's a process. So keep calm and carry on. So all I got for you. Again, like, I don't know how much time we have in here. I don't think it's that much, but like, I'm going to be available for the next couple of hours. If anybody had any questions that they were like, really wanted to know and were afraid to ask them to everybody, I'm happy to answer questions.
Are you going to be posting these slides somewhere?
I need to remember to do that. If I don't, you should ask me on Twitter like every day if I don't do it again. Okay. So I'm voting that I want to do. Any other questions? Good stuff. Okay, well, thank you. Oh, go ahead.
How does metal differ versus from OpenGL from higher level?
So there's a bunch of metal does things a little bit differently in the way that it encodes data to be sent to the GPU. So like when OpenGL was originally created, this GPU wasn't particularly powerful, so it tried to send as little work to the GPU as possible. But then over the years, the GPU has become incredibly powerful, and Metal has set up a different way of being able to encode all of its data to be sent to the GPU to make it more efficient to send work to the GPU and to do like certain work, like the shaders are compiled during your build time rather than during runtime. But also, OpenGL didn't really allow for general purpose GPU programming for things like neural networks and image processing. So it allowed, being able to use Metal over OpenGL means that it allows you to do different types of work on the GPU that use a lot of mathematics.
Do you go into that type of stuff?
Yes. Yes, about half the book is on the general graphics stuff, and then about the back half of the book is about the compute stuff. So yeah, I go into neural networks and image processing and machine vision. Good. Anybody?
All right.
All right. Thank you very much.